That's so we're very happy to have Arya Yae from the University of Oregon, and she'll tell us about star-shaped Nakajima Quiver varieties, parabolic Hitchin moduli spaces, and their holomorphic symplectic structures.
Thank you so much for the invitation to organizers for organizing this conference. So the start of this talk will be very similar to the last talk, like very, very similar. So in a sense, I'm lucky because I don't have to define something quite as thoroughly. This talk is about these two moduli spaces. One is the moduli spaces of what I call central levy parabolic Higgs bundles. And then the other is a quiver variety, which I think of as a moduli space of quiver representations. I'll talk about their constructions, and then I'll talk about a map to go from the quiver variety to the Higgs bundle moduli space. And I'll prove some properties about that map. And then I'll state my main theorem, which is about how the two holomorphic symplectic structures compare with each other under this map. I'll give some context in this special D4 case, and then I'll go into the proof strategy. So to begin, I always work in genus 0, so C is going to be CP1, and I'm going to fix a divisor D at n distinct points in C. I'm going to let E be a trivial rank R star vector bundle. And a parabolic structure on E is going to be a filtration for every fiber over one of the margins, just like we saw a second ago. So you choose a filtration of this fiber as well as parabolic weights. And I do not require these flags to be full flags, so they can be partial flags. And the dimensions of each level can vary depending on which puncture you're over. So to keep track of all the data, I use these R's. Rik is the dimension of Fik, and M is the multiplicity. That's the dimension of the associated gradient that we saw in the last. And I assume that the sum of the parabolic weights with multiplicity is 0. That's required for a reduction of structure group to S R. So to keep track of all this data, I'll create this quiver. So this is a star-shaped quiver in the sense that there's one central node and then branches coming out of the central node. And whenever I talk about these quivers, I want these dimensions to increase as you go towards the center, right? Just like the flag should increase. And so I'll say a parabolic structure is of type QR to keep track of that. A parabolic endomorphism of a parabolic bundle is just an endomorphism where when you restrict to the fibers, it must preserve the filtration. And a Higgs field is a section of the shape of parabolic endomorphisms tensor the twisted canonical bundle. So I allow order 1 poles on the divisor points. And I define this MQRF to be this configuration space of all degree 0 Higgs bundles. So a complex structure, or a holomorphic structure as well as a Higgs field. And I'm interested in the Higgs fields which are holomorphic. So I define this level set within the configuration space consisting of holomorphic Higgs fields. And when you have a holomorphic Higgs field, you can look at its residue at a point in D. And you can project to the levy part of the parabolic subalgebra. So I use this math rec L to keep track of that. So I have a map from this level set consisting of polymorphic Higgs bundles to the sum of the levies. And I want this to be in the center of this levy subalgebra. And I call these central levy Higgs bundles. It's the exact same as we saw just a second ago. And in fact, I want to fix them to be equal to some sigma in the center. So I'm going to just focus on the pre-image of this sigma. So this is the configuration space of holomorphic Higgs fields as well as adapted to this sigma. So I'm going to do an example. So let's say over a point Pi, the branch of the quiver has dimensions 4, 2, 1. And I'm just going to take the standard filtration inside of there. Then a Higgs field is parabolic if its residues look like this. It's kind of block operator. And the levy part is just the block diagonal piece. So if you just look at the block diagonal pieces, that's the levy part. And we want this to be equal to some element of the center. So in particular, each of these blocks should be scalar matrices, and I identify those with complex numbers. Finally, we have this notion of slope stability. It's kind of the usual slope stability. So it's about holomorphic phi invariant subbundles in their parabolic degrees. And we have this gauge group of invertible parabolic endomorphisms. And we take the alpha as stable locus and mod out by this G to define the moduli space. So this moduli space is a hyperkähler manifold, and its holomorphic symplectic form is given by this formula. There's a bit of an asterisk here, so this was worked on by several papers. Kohner does it in the strongly parabolic case, and then Picard-Bolch does it in the wild Higgs bundle case, but it specializes to the weakly parabolic full flag situation. And then Collier-Fredrickson Wentworth do a separate proof for the weakly parabolic full flag situation, but this central levy condition, it should adapt to that situation without too much modification. In this construction, we fixed a tuple of parabolic flags, and you could ask, what if you changed the flags that you fixed? Well, you could find a gauge transformation which takes one set of flags to another set of flags and translate all your data using that gauge transformation. And you will create an isomorphism between moduli spaces that way. And there's no ambiguity, so you can just define the moduli space without having to fix a flag. But my warning is that if you want to apply this formula for the holomorphic symplectic form, these deformations must be with respect to a single flag. So I call these fixed flag deformations. They shouldn't change the flag as you vary. Any questions about this construction?
Levy inverse is the moment map. So left LEV is the moment map. Yeah, you quotient out by the gauge field, right?
Yeah. So in theory, this should be able to be combined with the mu moment map that gives you holomorphicity. And you should combine that with the projection to levy to get a single moment map, but you need to work in some configuration space with distributions. I believe that works. I avoid that, and so I do the slightly clunkier version of it. Finish. Any other questions? Okay, so that's the first moduli space.
So, but why the gauge field is the gauge field is SL sigma. It's SLE.
That's LE.
But not the levy component.
Yes, this one does not. This can be just parabolic endomorphisms. Yeah. And because of the central levy condition, this preserves that level sense. So, thank you. Okay, so we have this quiver, and now I'm going to talk about the Nakajima quiver variety associated to this quiver and dimension vector. So a representation of this data is a collection of homomorphisms along each arrow, where you think of these as a like R-dimensional vector space for each node. You can take the cotangent bundle of this rep Q vector space, and elements of that cotangent bundle will have arrows going in the reverse direction as well. So homomorphisms X as well as Y. So you can think of these as representations of the doubled quiver. And this is the cotangent bundle of the complex vector space. So it has a standard hyperkähler structure. You have a real symplectic form and a holomorphic symplectic form, and that encodes all that data. And there's an actual complex Lie group acting on this space of representations. It just acts by change of coordinates on each node. So SL2 acts on the central node, and you have all of these remaining GLRs. This action is Hamiltonian with respect to capital omega, and so it admits a moment map, which goes from X to the dual Lie algebra. Since the Lie algebra is a product, or is direct sum, this moment map composes into decomposes into components. So you have this star component as well as all of these ij components, and I've written the formulas here. I will explore these more, but for now I want to say there's also a real form, a compact real form inside of the Lie group, and that is Hamiltonian with respect to little omega, and it admits its own real moment map. And similarly, as moment map decomposes. So moment maps are G-equivariant with respect to the coadjuvant action on the dual Lie algebras. So if you take central elements of the dual Lie algebras, the level sets defined by those central elements will be preserved by the group actions, respectively. So I call this the tau level set and the beta level set. And so we want to restrict our focus to these level sets, which means I impose these four families of equations. There's really one equation for every node, and then another equation for every node from 3. And then we define the Nakajima quiver variety to be this intersection of level sets mod the real Lie group. And for generic choices of beta, this is a smooth hyperkähler. So I'm going to explore one of these equations. So I'm interested in this tau level set equation. We'll use it a lot in this talk. So just to get our hands on it, I'm going to define this capital X to be the compositions xk through xl. In this picture I've drawn, think it's like the composition that ends at R star. And if you post-compose that with YL, then this lemma states that you can commute the Y past all of the X's, but you pay the price by picking up these taus. And I have this diagrammatic version of this picture. Later on for proofs, these diagrams can help us understand what's happening. So you read the composition right to left. And the proof is just because this one moment map equation says that you can commute Y past a single X, but you pay for it by picking up a tau. And so by this Kempf-Ness theorem, you can identify this quiver variety with the beta stable locus of the tau level set mod the complex Lie group. And this is much easier to work. And you still get the structure of the holomorphic simplex manifold to get this. So I'm going to define this notion of stability that is proven by King. So it works by extending the choice of betas. Remember, we have betas for every single node in the quiver. We extend it to the central node by choosing this particular weight. And then you define the beta weight of a representation to be kind of like the dot product between this weight vector and the dimension vector. So the weight vector has a weight associated to each node, and the dimension vector has a dimension for each node. And you just dot them. And so King's theorem says that in the GIT sense, representation is beta stable if and only if the beta weight of R is 0. And for all non-zero sub-representations, the beta weight strictly decreases. So it has to be a negative. And I have some examples of this. So let's consider this particular, I call this like a D4 type quiver. I'm going to assume that beta weights are all positive, and I'm just going to put them in order, beta 1 up to beta 4. So I have on the right here my weight vector. And I'm going to assume I have a representation in which all the y's are 0, but then the image of x1 and x2 are the same as each other. So I have two parallel vectors. Then I can define a sub-representation where in the central node, I just take the image of x1 or x2, and then I choose 0 for the remaining spots for 3 and 4. And when you calculate the beta weight, this will be positive, which means you've destabilized the original. In the geometric kind of polygon perspective that Professor Heller was talking about the other day, this represents having a polygon where you have two proportional side lengths that are longer than the sum of the remaining side lengths. So you kind of can't close up your polygon. So any questions? So my next example is just this single branch of a quiver. So I'm going to assume my weights are all positive again, and I'm going to assume one of these x's fails to be injective. Then I can define a subrepresentation by taking the kernel of that non-injective x, and then for each of the remaining nodes to the right, I just take the subsequent pre-images of that kernel. And you can show that this really is a subrepresentation, and its beta weight will also be positive, so you have these things. So as a result, for these quivers, every x must always be injective, as long as your weights are all positive. So we can now use a representation to construct a Higgs bundle. I'm following originally Godino and Mendini did this in that D4 case, and then Ryan and Shaposnik explored it further in the strongly parabolic case with additional assumptions on the betas. But I generalized to the weakly parabolic case too. So we construct the Higgs bundle. We take the holomorphically trivial bundle over P1. And for the filtrations, we take F to be the image of these compositions. And since they're all injective, this F will have the correct dimension. And then you define the parabolic weights by these two equations. So beta should dictate the gaps between parabolic weights. Similarly, you can use these taus to define the sigmas. Remember, sigma is what we're prescribing for the Levy part of the Higgs field residues. Use the same formulas. So tau should determine the gap between the two. And then you define the Higgs field by setting the residue to be this x times y, and then the trace-free part of that. So in this picture, this is just taking x and then y, or y and then x, and that's an endomorphism of ours. So it's the correct dimension. And this Higgs field that you construct, it will be holomorphic at infinity, and it'll also be adapted to the parabolic structure and have the correct Levy parts. The proof of that statement uses the two moment map equations. These are just the complex moment maps. So I'm going to do an example again. Once again, I'm going to assume a branch is like 4, 2, 1. And I'm going to assume I have a stable representation. Since all the x's are injective, I can choose a basis so that it looks like this, at least for one branch. And then the complex moment map equations constrain y to be like this. So you have these free entries, but the diagonal parts kind of are constrained. And when you use these to build a Higgs field residue, you get this expression. So this is x times y, and I subtract a multiple of the identity to make it trace-free. And when I simplify that expression, I get this matrix. And if you set these diagonal blocks to sigma 1, sigma 2, and sigma 3, you can see that those relations we talked about, where the gaps between the sigmas is tau, that all holds. So my first theorem is that if you add this assumption that the beta weights are sufficiently small, and you start with a stable representation, then this construction builds a stable Higgs bundle. And to prove that, we compare the degree 0 subbundles of the Higgs bundle with the subrepresentations of xy. And the combinatorics all lines up perfectly in that case. This additional hypothesis is required because there are also negative degree subbundles that could potentially destabilize a Higgs bundle. But by restricting the parabolic weights to be too small, that rules that situation out. And finally, if you have two equivalent representations, the resulting Higgs bundles are equivalent, so you get a map on moduli spaces. And it's all well defined. Are there questions about this map? So my next theorem is that this map T is a homeomorphism onto the locus of Higgs bundles with trivial holomorphic structure. This is a Zariski open subset of the Higgs bundle moduli space. So in particular, they have the same dimensions. Nakajima provides this dimension count using geometric invariant theory. And this shows that this is another way to see that the dimension of M is the same. So a natural question is, what quivers would lead to a four-dimensional moduli space? And I have this picture here. So it turns out these are the quivers that lead to four dimensions. And you plug it into the dimension formula, you get four. And you'll recognize these as the D4, E6, E7, and E8 quivers with their labelings. And Nakajima shows that the quiver varieties are ALE gravitational instantons. And the corresponding Higgs bundle moduli spaces should be ALG, but that's still conjecture and hasn't been proven in all those cases. So we have two holomorphic symplectic structures on these two spaces. We have omega x and omega m, given by these formulas. And my main theorem says that this map T relates the two holomorphic symplectic structures in this way. So up to the constant 2 pi, it identifies the two holomorphic structures. And the 2 pi is really convention. You could just scale down your metric on one of the spaces. And as a corollary, you have these Hitchin vibrations on M. And so you can pull that back through this map to get an integral system structure on X. Any questions about the main thing? Generic fibers. I would need to think more in the central Levy case that's more general. But in the strongly parabolic and full flag cases, it should be a doing for these. Well, for the pulled back one, it's affine.
So is it true that if you take the analytical open locus of the M, then you can get the Nakajima quiver variety, star shaped Nakajima quiver variety, just as pi you denoted?
So you say that the analytic
open set, or yeah, you just take a like sufficiently small analytic open locus of the M of the parabolic Higgs moduli. Then is it true that you can get the star-shaped Nakajima quiver variety?
And can you say what you mean by like how you get it? How you get the quiver variety?
Well, if you,
I'm not sure.
you can, yeah, just as the modular space is the hyperkähler manifold.
The full hyperkähler structure will not agree.
Okay.
Yeah. Just the holomorphic symplectic structures. Sorry.
What symplectic structure? Oh, okay, I see. Thank you. But as the holomorphic, okay.
Any other questions?
So you inject the quiver variety representations, the modular space. Is there an in some open, trivial holomorphic, right? Is there an interpretation in terms of the quivers of the rest of the modular space of Higgs bundles?
I've tried to look for this, and as far as I can tell, there's not. You mean where the holomorphic structure changes, whether there's a quiver? I've looked, and I have not been successful in finding a way to describe these other strata as quivers. So I'm just going to give some historical results. So I'm going to focus on this D4 situation. In the D4 situation, it has been explored quite a bit. So Godino and Mendini originally proposed this map T and showed that it's well-defined. And then Biswa, Florentino, Godino, Mendini showed that they proved the analogous result, that it preserves the holomorphism. But it needs the strongly parabolic situation, which means tau and sigma are 0. And then Laura Fredrickson and I, as well as Kelly Heller and Menezes, show that there's a family of full hyperkähler metrics on N, which converge to the hypercalorimetric on the Quiver variety under a certain degenerate limit. So the hyperkähler structures don't match, but you can create a degenerate limit to make them free. But all of that assumes strongly parabolic. And there's a theorem by Nakajima that says that as you vary tau and beta, you can exhaust all the ALE D4 instantaneously.
It's Kroheimer's.
Sorry?
It's not Nakajima, it's Kroheimer's.
Kronheim. Oh, sorry. Yeah, and so this is not just the ALG-D4, but it's ALEs. And then Fredrickson, Matteo, Swoboda, Weiss are working on proving a similar theorem for the Higgs bundle moduli spaces. They're partway there. They have part one of a series of papers which should achieve this. Currently, there are details that remain. But the point is that you have to vary tau and sigma in order to get the full class of ALE and ALGs. So the strongly parabolic case is not enough to cover the full moduli spaces. So that's part of why I care about the weakly parabolic situation. Okay, so I'm going to talk about the proof strategy. So how do you pull back a symplectic form? You do it by pushing forward tangent vectors. So I consider a path of Quiver representations a smooth family, which represents a tangent vector in the moduli space. And I want to apply T to this family to get the family of Higgs bundles. I need to perform a gauge change to hold the flag fixed. And then with the flag fixed, I can calculate the first variation to get this fixed flag deformation. And that's ready to be plugged into omega. So I do this simultaneously to a pair of deformations. And then I produce this A and this phi, and I plug it into omega. And the goal is to prove that that integral results in this. So I need to describe this gauge change then. And I only need to describe it up to first order. So it's kind of a funky definition, but I want this endomorphism mu to induce the first variation of the flag. And what it means is that if your flag is changing and you have any smooth family of Higgs fields which is changing with it, conjugation by this e to the t mu shifts it back. So up to first order, the flag is no longer changing. And it does that for any choice of Higgs fields. And so I need to find this nu to create that. But once you do, you take the nu and you conjugate this data, the holomorphic structure and the Higgs field, and you produce your A dot and your phi dot. So you can give it all in terms of this state. Okay. So we do this again to just an arbitrary deformation. I'm going to use this notation capital X again for the composition. And since I know it's injective because of stability, it has a left inverse. And so I take nu. I choose any nu. It only matters the values of nu at the punctures. But I take any continuous nu, which at the punctures satisfies this formula. These terms, which I call B, they can be represented diagrammatically this way. And the key property that they satisfy is that if you take an xj for j less than k, and you post-compose with b dot, it kind of inserts an x dot partway through. So it takes this xj and it inserts a dot at the k. So somehow it's describing the changing. So unfortunately, I can only give you the full proof in the strongly parabolic case. In the weakly parabolic case, it's like 6 pages of painful calculations. In the strongly parabolic case, you have these tautological one forms whose exterior derivatives are the holomorphic symplectic forms. And so we just prove it for these tautological one forms. We prove that the pullback is 2 pi times the. That way you don't need a pair of deformations, you just need one. So I'm going to let A dot and phi dot be this fixed flag deformation like I discussed. And I plug it into L. And this is just the definition of L first. And then I use the definition of A dot, which has this del bar nu. And then because phi is holomorphic, there's no product rule to worry about. So you can apply Stokes' theorem to this to recover this residue. 2 pi times the sum of these traces. So my goal now is to show that the trace of that product is equal to the sum of these traces. You see there's a single sum here, but a double sum here. So I need to introduce that additional sum. But I have an explicit formula for nu dot of p. So I plug that in, and I introduce this sum in terms of k, the b's. I plug in the formula for b dot, and then I use the cyclic property of trace to move this x over to the other side. And then I commute the y past all of these x's, using that rule I discussed earlier. There's no tau to worry about because I'm in the strongly parabolic case now. And now since x to the minus k is a left inverse of x to the k, they cancel, and I got this as a result. And there's that diagrammatic calculation for this. And so altogether, we've calculated the pullback of the one form by pushing forward the deformation and then plugging it in and simplifying. And we got the one form on the quiver varieties. To prove this in the weakly parabolic case, it's more complicated because now there's 2 deformations and there's just many more terms to worry about. But after doing all the hard work, you end up with the same result. That concludes the talk.
At the site of the parabolic Higgs bundles, you could consider some other reductive group, in particular classical, right? Instead of SLNC. So you have everything there. And I suppose in the quiver side, you will have Nakajima quivers with some symmetries, right? I mean, at least in the classical groups, right? Have you thought about that?
We have
I wonder what this gives in terms of the ALE instantons or something.
yeah.
Gravitational instances.
I'm not sure. I haven't considered the quiver varieties as groups in this idea.
Yeah, I consider my I consider I introduced the evolution of the
Evolution,
I
of
think
course.
take a fixed.
You can do both. You can consider holomorphic involution or even some reality structure.
That's maybe interesting.
And you related the modulation version of parabolic module of Quiver, right?
Yeah, so Brian and Shatopsnik explore this. So they add loops on the center node, and then they propose the map. I've had trouble verifying certain details of it, so we can talk about it. I suspect that you might need to consider like multi-quiver varieties of some kinds to make it work. But it seems a little less explicit, whatever the construction would be, because you somehow prescribe the holonomy.
If there are no other questions, let's thank the speaker again. Great.